The unit circle. This video will help you identify angle measures in the unit circle, become familiar with the 6 trigonometric functions, and become familiar with the Pythagorean identities. The unit circle. Let's take a look at a definition here. The unit circle is a circle with a radius of length 1. That's why we call it the unit circle, because the radius is of 1 unit in length. The equation of this circle is just our equation for a circle. Remember, x squared plus y squared, and whatever value we have over here is the radius of the circle. Since we're on the unit circle here, that's going to be 1. So the sine function, our first trigonometric function, the sine of theta is equal to y. And what that means, now theta is an angle here, and as we travel around here, this is our unit circle. Notice if I look at the radius, I start at the origin, I'm coming out here a unit of 1. So if I put this circle on our coordinate plane, then notice we have our first coordinate here, an x coordinate of 1 and a y coordinate of 0. And so as we travel around here, still of radius 1, travel around the circle, up here, an x coordinate of 0 and now a y coordinate of 1. Well, basically what happens is we define this sine function to be all of the y coordinates we get as we travel around the circle, this little unit circle of radius 1. So if we look here, you know, these are our ordered pairs here. Here's x and here's y. And so these are all my y values here. And so you notice my y value of the first point starts out at 0 and then begins to climb. So it goes from 0 to 1/2 to the square root of 2 over 2, square root of 3 over 2, all the way up until it reaches this maximum value of 1. And then notice my y coordinates are starting to then decline until they come all the way back down to 0. Then my y coordinates travel down here to negative, and then finally come back up to 0. And every time I travel around the circle again, those values, those y values repeat. And so that's what a trig function is. It's defined to be just these y coordinates, at least the sine is defined to be just these y coordinates as we travel around this unit circle. Okay? The cosine function, abbreviation for that's COS, and sine is SIN. The cosine function of theta, so again, same theta that we're looking at now, and all cosine is just the x coordinates. So notice if I start here at 0, a theta value of theta of 0, my x starts out with a value of 1, so notice that that's the maximum x value I get here. Then it starts to decline. So 1, square root of 3 over 2, square root of 2 over 2, 1/2, and then all the way down to 0. And now x is going to start to climb, decrease negatively. So now we're starting to head in the negative values until we get to -1. Kind of our least value there is -1. Then it starts to rise and climb back up. Now we're just talking about x coordinates here, so this is actually increasing all the way till it gets to this side and comes back to 1 again. And so that's what the cosine is, just all of the x coordinates that we get as we travel around the unit circle. Okay, and again, theta is just the measure of these angles, and we studied these same angles in our last unit there. Notice 0, 30, 45, 60, and 90, and those same kind of increments repeat. You notice the placement of these angles are the same in every one of these quadrants here. And so those are the typically, now there are values, of course there are x and y values in between these ones we've identified on the circle here, but we usually don't use those quite as much in trig. They'll come into play when we're kind of dealing with real life application situations, but for the most part, when we're just practicing and working on our trig, we just use the values here that are on our unit circle. Alright, let's see, what else can I tell you about our unit circle? Notice we got our degrees in here, and then we've also got our radians on the outside, and we just got done studying radians. You're going to want to make sure you know both the degrees and the radians, but really it's pretty easy. If you just get this first quadrant down, then all we would have to do to get the second quadrant is take 90 degrees and add it to these degree values, or take pi over 2 and add it to these radian values to get the second quadrant. The third quadrant, all we have to do is start at either pi or 180 and then add those same values again to get the third quadrant. And here, if we're trying to get the fourth quadrant, we just start at 270 degrees or 3 pi over 2 and add those values up. So the unit circle is very repetitive. And notice that, these angle measures, as we learned in the last unit, can go past 360 degrees, or they can go past 2 pi and start to cycle around again. And so we get this repetition in these sine and cosine functions, and they actually have a lot of real-world applications, because there's a lot of things in the real world that we would try to model using mathematics that happen periodically or cyclically. And so that's when these functions come into play. All right, let's talk about the unit circle, because this is something that we're going to need to know. So you're going to need to know the degrees. Here we're going to need to know all of these degrees, starting out at 0, 30, 45, 60, 90. And again, once we learn this first quadrant, we pretty much get all the other ones for free. We're going to have to learn the radian measures here. 0, and then pi over 6, pi over 4, pi over 3, and then pi over 2. But notice, as we discussed last time, these are just repetitions. If I start at 0 and I go to pi over 4, and then I add another pi over 4, notice I get to pi over 2. So really, we're just taking this pi over 4 and doubling it, or adding it again to get to this next space. And if I wanted to get this next red mark over here, I'd add pi over 4 again, pi over 4 again, pi over 4 again, so on and so forth. Here, we're just going to add pi over 6. If I take this distance of pi over 6 and I add pi over 6 again, I get 2 pi over 6, which is just pi over 3. So really, on this unit circle, we really only have two kind of starting points with measures here that we keep repeating. It's the pi over 6 and the pi over 4. Notice, if I take pi over 6, I'll get pi over 6, pi over 3, and if I add it again, I'd end up at pi over 2, then 4 pi over 6, which is 2 pi over 3. Again, it just keeps repeating for the blue one there. That's why those are highlighted in blue, because those are all the values, or all the angle values that are an increment of pi over 6, and the red ones are just an increment of pi over 4. Okay, let's talk about the sine and cosine values, because this is something we're going to have to know as well. So notice, x is my cosine, y is my sine. And so notice y starts out at 0, climbs to 1, x starts out at 1, and then decreases to 0. And so there's a real simple pattern here that's going on. These values have been simplified, a lot of them. But if I write down what these values are with the square roots in, then you'll see the pattern here. So if I start out with 0, and I say, instead of 0, I say that's the square root of 0 over 2. And instead of simplifying this one here, I say that's the square root of 1 over 2. Notice, square root of 0 is 0. That's where that comes from. Square root of 1 is 1. That's where that comes from. Then notice, if I write the next one, it's the square root of 2 over 2. Then the square root of 3 over 2. And then finally, when we get up here to 1, that's the square root of 4 over 2. Because, of course, square root of 4 is 2, and 2 divided by 2 gives us 1. But you can see the pattern here that's happening. So y, or my sine, starts out at 0, square root of 0 over 2, then goes to square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 root of 2, and then it starts to decrease coming around the other side using these same values again. So this value is right here, this value is right there, and again, it just repeats as we work our way down. Notice this same pattern holds true for my x or my cosine values, except it's in reverse. So here, this is the square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, square root of 0 over 2. And that's a real easy way to memorize the sine and cosine values. Now, we don't need to memorize more than the first quadrant, because they just repeat. So for example, if I'm doing my y values here, or my sine values, this location here is 1/2. Well, this location here is also 1/2. Notice the y coordinates of this and this are the same. Now, if I came down to the other side, these are kind of the corresponding values down here for these y values. Notice they're going to be the same, except now we're going to be negative, because we've traveled below the origin here, or sorry, below the x-axis. So we're going to be negative. So notice, we had a positive 1/2. Down here we have a negative 1/2. Same is true over here. Okay, so once you get the first quadrant, you really get all of the other quadrants. You just got to pay attention to the signs. Notice, first here, x was positive, right? Over to the right of the origin here, x is all positive. So these values are decreasing, but then once we get here, we're going to get negative. Notice, going to get the same values, positive 1/2 here, but negative 1/2 here, because now we've crossed over the y-axis, and these are going to be negative x values. So really, you can get all of these values pretty easily. 30, 45, 60, 90, those are pretty easy to remember too. And this pi over 6, pi over 4, pi over 3, maybe a little trickier, but after a couple times practicing it, you'll get the hang of that. But to do the trigonometry, we're really going to have to give a good handle on this first quadrant and have that first quadrant memorized. So what you need to do is, as you're practicing all of this stuff, is test yourself. Every time you need to find a value on a unit circle of some sign, of some kind, an angle or an actual value for sine or cosine, go ahead and guess first and test yourself every time. And after a while of guessing and checking and guessing and checking, you'll start to memorize these things and you'll have the unit circle down. All right, here's a great chance for you to do that. So we just talked about a lot of things here and a lot of information, but I think you're in a spot now where you could fill most of this out. So I'd like you to fill out just the first quadrant here. We're only focusing on the first quadrant of the unit circle. And let's see, angle measure in degrees, angle measure in radians, and the value of the sine and cosine at each angle. So I think just like we did last time, maybe write the degrees on the inside here, then the radian measures on the outside, and then use some ordered pairs here on the outside to put in the values for sine and cosine. When you're putting in the values for sine and cosine, I think it would be an advantage not to simplify them right now. Just kind of use that pattern I showed you and try not to simplify them. I think it'll make it easier and be a good starting place for you. All right, so go ahead and pause your video player now and fill this out. And when you get done, hit play and see how you did. Okay, so hopefully you got most of these correct. So if we look at our degree measures here, we go 0, 30, 45, 60, and then up to 90. If we look at our radian measures, 0 here, pi over 6, pi over 4, pi over 3, pi over 2. If we look at our x-coordinates now, which is our cosine values, we start out with our greatest x-coordinate here of 1, which is just the square root of 4 over 2, and then they just decrease then. Square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, square root of 0 over 2. And then if we look at our y-coordinates here, notice y starts out at 0, so square root of 0 over 2, and then increases as we go up. Square root of 0 over 2, square root of 1, square root of 2, square root of 3, square root of 4. So hopefully you were able to get that. Okay, so the sine and cosine and all of our trig functions are called periodic functions because they go through a period and then they repeat, and go through a period and then repeat. And so let's start here first with our sine function, and you can see what happens. Remember, we just did this. So when we started at an angle of 0, our y-coordinate there was 0, and then it starts to increase. So then we go to pi over 4, it's increasing. Pi over 2, it reaches its maximum value of 1, and then the y-coordinates start to fall as we travel around the circle. Decreasing 3 pi over 2. When we get back to pi, then we're at 0. Notice up here, if we kind of scroll back up, you know, this is what we just did. Y started at 0, increased to 1, then falls back down to 0, and now we're going to start to travel in our negatives here, our negative y-coordinate values. And you can see this graph traveling down now. Y decreases now, my sine decreases, and then starts to climb again and goes back up to 0. And this whole period takes one time around the circle. Remember, in one time around the circle in radians is 2 pi. So this whole cycle then would repeat again. We'd start out here at 0, and then it would start to climb and continue on just the same way it did. So sine is a periodic function, and we would say the period of the sine is 2 pi, because after every 2 pi, the function starts to have repeating values, and it repeats the same graph or the same values here. Okay. Same thing is true for the cosine. It also has a period of 2 pi, except its values are a little different. Notice my x-coordinates start out at a maximum value of 1 and then start to decrease. So they start to decrease, they get to 0, pi over 2, and then we go into the negative values until we reach our minimum value at pi, which is -1, and then they start to climb again, and that whole cycle then would repeat again for the cosine. Okay, there are other trigonometric functions. Tangent, cotangent, secant, and cosecant are all based on the sine and cosine. So sine is the y coordinates as we travel around the circle. Cosine is the x coordinates as we travel around the circle. All of these other trig functions, tangent, cotangent, secant, and cosecant, are based on sine and cosine. And of course, sine and cosine, they're really simply just the x and y coordinates we get when we travel around the circle. So this is all kind of like very, starts out kind of as real basic stuff. And as we're learning this trig, oftentimes you're going to have to kind of take a couple steps back and go back to kind of the simple beginnings here to figure out what's going on. I think this unit circle and understanding that sine and cosine are just the x and y coordinates, you can figure pretty much most everything out from there if you start at that place. So some of you guys have already had some experience with trig functions, tangent, cotangent, secant, and cosecant. And here are the abbreviations down here: tangent, secant, cotangent, cosecant. They're defined in terms of sine and cosine. Some of you guys might remember this. So let's go ahead and take a second. Pause your video player. If you can remember any of these things here, any of these, go ahead and list them out. If you get them wrong, you can always erase them, but go ahead and give it a shot first, and then hit play to see how you did. All right. Well, tangent is just sine of theta over cosine of theta. Cotangent is the inverse of that. It's cosine of theta over sine of theta. Secant is the inverse of the cosine. So it seems like it should be kind of going with the sine. I don't know what's going on with the language here, but it didn't work out that way. It's 1 over the cosine of theta for the secant, and the cosecant is the same way. You think it should go with the cosine, but it doesn't. It actually goes with the sine. It's 1 over sine of theta. So that's how we define all of these. So given an angle measure here with tangent, if we knew what the angle measure was, like let's say pi over 4, you could evaluate sine at pi over 4 and cosine at pi over 4, and then from that, find the tangent value at that location. Okay, so let's take a look at the tangent. Remember, the tangent of an angle is sine of theta over cosine of theta. And so this is a little different sort of graph here when we look at the tangent, but you'll see why we end up with what we end up here. So if we started at tangent of 0, and I'm looking right here at my graph, tangent, when I put it up, plug in a value of 0, sorry, not tangent of tangent, but tangent of 0 here, I'll get the sine of 0 over the cosine of 0. I don't know why I keep doing that. Cosine of 0. Well, the sine at 0, remember, was my y coordinate, which was 0, and the cosine is 1. So I get 0 over 1, which just equals 0, and you can see that's why we're getting this point here. Now, from here, then, as tangent starts to increase, like we get the tangent of, let's say, pi over 4. One thing happens really unique at pi over 4. Sine and cosine are both the same. They're both square root of 2 over 2, square root of 2 over 2. That's what happens at pi over 4. And anytime I take a value divided by itself, I just get 1. So here at pi over 4, which is right here if I'm at 0, halfway between, this would be pi over 4 right there, coming up with a value of 1. And you can see this thing is getting really growing very big very quickly, and here's why. What's happening here is if we looked at the tangent of pi over 2, at pi over 2, this kind of scenario here is reversed, because at pi over 2 now, sine is 1 and the cosine is 0. And so we end up with this being undefined here, this tangent of pi over 2, 1 over 0, we can't divide by 0, and we actually get an asymptote here. And those asymptotes just repeat every pi over 2. Sorry, every pi. They repeat every pi. So if I have my one asymptote at pi over 2, my next one will be here at 3 pi over 2. Okay, and so what's happening here, so why this thing is taken off to go towards infinity, is because my x-coordinates or my cosine coordinates are getting really, really small. As I get close to 0 here, as I approach pi over 2, this value gets super tiny. And if I take 1 and divide it by a very, very small value, this can actually take off to infinity. And that's why we have the graph here, taken off to infinity. Same thing happens as we approach negative pi over 2. As we approach tangent of negative pi over 2, then we get this, except we get negative 1 over 0. So again, we get another asymptote here. And again, as we approach this negative pi over 2, my cosine values are going to getting really, really small. And negative 1 divided by a really, really small number actually goes off to negative infinity. So that just kind of gives you an idea about the graph of the tangent and why we have asymptotes in there and why these graphs take off to infinity and negative infinity. So let's see, I've got a question here for you. Okay, so now let's take a look at question 3. Go ahead and think about that question. Use the graph to determine one period of the tangent function. And why don't you tell me also what the period is. You know, every period has a starting point and an ending point. So why don't you tell me the length of the period and then also starting point and ending point. So go ahead and pause your video player and answer that question. When you get done, hit play to see how you did. So one period of the tangent function, notice the tangent function here kind of starts to repeat itself. It starts at negative pi over 2, kind of where this pattern occurs. Then it comes up here and occurs again. So if we look at this duration from here to here, that's a period. Negative pi over 2 to pi over 2, if we think about that, here's negative pi over 2, and then 0 in between, and then positive pi over 2. That is an overall distance of pi here, because it would take me pi over 2 to get to 0, and then another pi over 2 to get there, and pi over 2 plus pi over 2 is 2 pi over 2. So that period for the tangent is pi. This period is pi. Now, there's lots of ways to kind of think about this period and the way it repeats itself. You know, there's definitely an argument to say we could start at 0 and travel out to pi, and this thing would start to then repeat itself again. But I think when we're looking at the period of these functions, we want to try to grab like the whole graph or a complete version of the graph. And I think if we're going to do that, the best way to think about a period for the tangent is between negative pi over 2 and pi over 2. It's kind of our starting place, or our recognition of one period of the tangent function is from negative pi over 2 to pi over 2. All right, moving on here. So the cosine, secant are even functions. The sine, tangent, cotangent, and cosecant are odd functions. And that makes sense because remember, if I say the cosine is odd, remember the secant is just 1 over the cosine. So that makes sense. Sorry, these are even, not odd, even. These guys are even. But it makes sense if one of those is even, then the other one would be as well. And the sine, of course, is odd. So that one goes with the cosecant because those are inverses of each other. And then as it turns out, both the tangent and the cotangent are also odd functions. Now we know a couple things about even and odd functions, so let's go ahead and pause your video player now. And why don't you give me some attributes of even and odd functions. Things that we know about a function when it's even. Things that we know about a function when it's odd. So go ahead and pause your video player now and write those down and hit play to see how you did. All right, even functions. They're symmetric across the y-axis. And we know that if we take f of negative x, it's the same as when I evaluate a positive x in there. Odd. They're symmetric across the origin. And again, the origin is across the lines, either y equals x or y equals negative x. That's what we mean by origin symmetry. And we know that if we take f of negative x, we get exactly the opposite value in an odd function. So those are going to come in handy here as we're working on some of these trig identities and trig problems that we're going to be solving here. Okay, when we replace x and y in the equation for the circle, remember this is an equation of a circle of radius 1. X squared plus y squared equals 1 is a circle with radius 1. And we replace y with the sine and x with the cosine, we get our first Pythagorean identity. And it's cosine squared plus sine squared is equal to 1. And Pythagorean identity, if that sounds familiar, it is, because this is the Pythagorean theorem about a triangle. So if I looked on my circle here, and I picked some point here on my circle, and I drew a triangle to this point. So I will draw this. This would be the radius. And if I draw this leg down here, notice this would be, this distance here would be my x-coordinate. So there's my x-coordinate. This distance here would be my y-coordinate of that point, right? This point here would have a value of over x up y. We know the value of the hypotenuse of this triangle because that's also the radius of our circle. That's 1, we said. And so you can see here in our little triangle, leg squared, x squared plus y squared is equal to the hypotenuse squared. That's the Pythagorean theorem. And so we use Pythagorean theorem here when we talk about trigonometry and we're working on the unit circle. It's just that most of the time when we do this, our radius here, or our hypotenuse of the triangle, will be 1, which actually kind of simplifies things for us a little bit. So that's why we call this a Pythagorean identity. So we use Pythagorean identities to help us solve trigonometric equations and verify trig identities. What they do is they allow us to substitute one trig function for another, which will help us to solve equations and also help us to verify and prove things. We're going to be doing some proofs as we're studying trigonometry. And so this will help us to do that. So here are our 3 Pythagorean identities. Cosine squared plus sine squared is equal to 1. 1 plus tangent squared is equal to secant squared. And 1 plus cotangent squared is equal to cosecant squared. Now, as I mentioned here before, that we can use the first one to derive the others. We can use this guy to derive the others, and that's what we're going to try to do right now here in question 5. So what I want you to do is start with this statement here, cosine squared plus sine squared equals 1. We know that's true because Pythagorean proved that to us. We know this thing up here in our triangle. This was the Pythagorean theorem. Pythagoras went through and proved that this would always be true in a right triangle here, that leg squared plus leg squared is equal to the hypotenuse squared. So that's a proven fact here. What we want to do is we want to use this proven fact now to show that this is also true. Now, to make this proof or to verify this, which is what we're doing when we're deriving this, all we're going to do is use some simple algebra here. So what I want you to do is I want you to take this equation, which we know is true, use some of our properties of algebra. We know we can add the same thing to both sides. We could divide both sides by the same value, those sorts of things. Use our properties of algebra here to derive or come up with this statement. So go ahead and pause your video player here now. This is a real kind of funny thing. When we're doing proofs, you kind of just guess and check. You say, ooh, here's an idea, try it. You give it a shot. If it goes somewhere, then you kind of work on it and maybe it leads to something. If you try it and it doesn't work at all, well, that's okay. Then you try something else. But what you don't want to do is sit there and stare at a blank piece of paper or wait for me to do the problem. You'll never learn to do these derivings or proofs or anything like that. So you just go ahead and go for it and explore and see if you come up with something. It's kind of like solving a puzzle. You just try to put some pieces together and see if it works. And if it doesn't, try 2 other pieces. So go ahead, pause your video player now and give this a shot. All right, so we're looking around here. We know that we need to have one of the trig functions on one side and then a trig function on the other. So maybe the first thing I might try, let's see, is I might try subtracting. Ooh, I want it to add too. All got to be positive. I don't know. Let's see. Well, let's see if I subtracted cosine squared from both sides. Cosine squared from both sides. Then I'd have this. Sine squared theta equals 1 minus cosine squared theta. Well, I know that I'm supposed to have the tangent in here somehow. And I know this. I know that tangent squared is sine squared over cosine squared. Because remember, tangent is just sine over cosine. So the squared would be sine squared over cosine squared. So maybe what I'd do next is maybe try to divide by cosine squared, because then I'd have sine squared divided by cosine squared. So I'll divide both sides, but remember, when I divide, I got to divide every term. So if I divided this one by cosine squared, I'd also have to divide that one. So let's see, divide by cosine squared theta, divide by cosine squared theta, cosine squared theta. Well, this part worked out because that's what I was kind of shooting for there. That's tangent squared theta. Let's see, 1 divided by cosine squared. Well, that is the secant squared. So that's kind of working out here. Secant squared theta. Cosine squared divided by cosine squared would be 1. So that's just going to be minus 1. So hey, I'm getting pretty close here. It looks like what I did here is I first subtracted cosine squared from both sides. That's a valid algebra property. Now I divided both sides by cosine squared. And the last thing I'm going to do here is add 1 to both sides. That's valid. Let's come over here. Then I'd have 1 plus tangent squared theta is equal to secant squared theta. And so there I've shown it. Now, one thing that I want to do here, my penmanship is not so good in the video here, but one thing I'd want to do, I was this is kind of scratch work here, and I was kind of just going through and looking that stuff up. Now what I might want to do, once I've kind of found the path here to make this happen, is I'd go back through and I'd clean this thing up so it looks very clear to the reader, because one thing we want to do when we're doing a proof or deriving something is we want to show to the person reading it that they can understand your work every step of the way. So I kind of figured out what I'm doing here. I'm going to go back through now and clean this up a little bit. Notice here I added 1 at the end too. I think if I just started out by dividing by cosine squared first here, it might be a shorter path. And that happens a lot of times when we're doing a proof or deriving something, is your first attempt might be a longer path than is necessary. So I'm going to go back through now, and I'm going to just, of course, if this was scratch paper, I'd keep it off to the side so I didn't forget what I was doing. I wouldn't encourage you to erase your stuff. But once you get it here, let's go ahead now and clean that up a little bit. And like I said, I think I'm going to divide first. So divide both sides by cosine squared. And as we're dividing, we've got to divide every term. And I'm going to line up my equal sign here so it's easy for my reader to follow along with what I'm doing. So I divide cosine squared by cosine squared. That's going to be 1. And then sine squared divided by cosine squared. Heck, that is tangent squared. And then 1 over cosecant squared. Wow, that's secant squared. So you can see when I rewrote it this next time too, it was a lot cleaner. And then one thing that we kind of like to do in math when we get this thing done is we say, oh, hey, it worked. I showed you what was going on, and we go a little check down there that says, hey, we showed that we got what we were looking for when we were trying to derive this. Okay, let's take a look now at question 6. Given the fact that cosine of theta is equal to 3/5, and that theta is between 3 pi over 2 and 2 pi, find the value of sine theta using one of the trigonometric identities. Alright, so what we want to do here when we get a question like this seems a little tricky. We know we want to use one of the trig identities up there, and we know this, so we don't want to ignore this piece of information. So theta, which is our angle, remember, is between 3 pi over 2 and 2 pi. So let's do a couple things here. Let's draw a little sketch of the unit circle. And why don't you get a general idea where this theta angle is? If you got to scroll back up and look at our unit circle again to figure out where exactly this thing is falling, go ahead and just draw a little sketch of theta, and then go ahead and look back there at some of the trig identities you've written down. Notice we're trying to combine some information about the cosine and find the sine. I think that will give us a little hint there too. So kind of put that information together there and try to solve this problem. When you get done, hit play to see how you did. Okay, let's take a look. Well, I'm going to start right here. I know that theta is between 3 pi over 2 and 2 pi. So here's 3 pi over 2 and here's 2 pi. So theta, let's just say, is somewhere down here. So this is my angle theta. It's coming around like this. It's opening quite a ways. So we know it's down here in the 4th quadrant. Okay? And we're kind of knowing that cosine here is 3/5. And we want to find the sine value. Well, all right, so let's take a look. So I think our trig identity that combines both sine and cosine is that sine squared plus cosine squared theta is equal to 1. I think that's all I would need, almost all I would need to have to solve this. So let's see. So we know that cosine is 3/5. So let's put 3/5 in there for the cosine. Squared is equal to 1. And then sine squared theta. All right, so I'm going to go ahead and square this. That's going to give me 9/25. And then I'll subtract 9/25, not add it, but subtract it from both sides. And then I would know then that sine squared of theta is equal to, let's see, 1, I'm thinking of 1 as 25 over 25 minus 9/25 is equal to 16/25. So I know that sine squared is equal to 16/25. So to undo squaring something here, I'm just going to take the square root of both sides. And so then I would know that sine of theta is equal to, now remember, when we're solving for something squared, it's either plus or minus here. Looks like 4/5. That worked out nice. Okay, so sine of theta is, we get two possible answers here, plus or minus 4/5. Let's look at our information to figure out which one it is. Well, they told us that theta here was between 3 pi over 2 and 2 pi, meaning down here in the 4th quadrant. Remember, sine is my y values. So my y values down here, notice where y values are dropping down below the x-axis, they're going to be negative. So we know that sine of theta is going to have to be negative 4/5 based on where theta is located. You know, had theta been up here in the 1st quadrant, we would have chosen the positive answer for that. But since it was down here in the 4th quadrant, we want to pick the negative value